Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn about the thermistor. So during the video, we will see the types of thermistors and we will also see the different applications of the thermistor. So this thermistor is a thermally sensitive resistor, and as you can see, from that only its name is derived. So it is basically a semiconductor device whose resistance changes with the temperature, and that is why it is used as a temperature sensor in the many applications. So this is the international symbol of the thermistor, but sometimes this symbol is also used for the thermistor. So in the normal resistor, if you see, then with the change in the temperature, there is only a small change in the resistance value. And for most of the applications, we can say that the resistance value fairly remains constant. But in case of the thermistor, if you see, then with the change in the temperature, there is a large change in the resistance value compared to the normal resistor. So for the temperature sensing application, by measuring this change in the resistance value of the thermistor, it is possible to measure the ambient temperature or the temperature of the medium where this thermistor is placed. Now in the normal resistor, if you see, then with the increase in the temperature, the resistance also increases. Of course, as I said, this change in the resistance is very small, but with the increase in the temperature, the resistance also increases. So we can say that the normal resistors have a positive temperature coefficient of the resistance. But if you see the thermistors, then they can have both positive as well as the negative temperature coefficients. So based on the temperature coefficient, we have two types of thermistors. That is the NTC thermistor and the PTC thermistor. And as its name suggests, these NTC thermistors have the negative temperature coefficient, meaning that as the temperature increases, then the resistance of the thermistor also reduces. On the other hand, these PTC thermistors have the positive temperature coefficient, meaning that as the temperature increases, then the resistance of the thermistor also increases. And these are the symbols of the NTC and the PTC thermistors. So in the NTC thermistor, as you can see, there is a minus T sign, while in the PTC thermistor there is a plus T sign, which shows that the NTC has the negative temperature coefficient while the PTC has the positive temperature coefficient. So these thermistors are made up of the metal oxides. So these oxides and the other additives decide the characteristic behavior of this thermistor. So these are the common materials which are typically used in the NTC thermistor. And similarly in the PTC thermistors, the materials like barium lead and the strontium titanate are used. So because of their higher temperature sensitivity, these NTC thermistors are mainly used in the temperature sensing applications. But apart from that, at the low to medium powers, they are also used as a inrush current limiter. And apart from that, they are also used in the level sensing applications. On the other hand, the PTC thermistors are used in the applications where a sudden change in the resistance is required at a certain temperature. So typically, they are used in the overcurrent protection as well as in the time delay applications. So depending on the temperature range and the applications, these thermistors are available in the different packages. So now, let us see the temperature versus resistance characteristic of this NTC and the PTC thermistor. And let us understand how they can be used for the temperature sensing as well as the other applications. So first, let us see the characteristic of the NTC thermistor. So as I said earlier, in this NTC thermistor, as the temperature increases, then its resistance reduces. But if you see its characteristic, then it is not linear, and rather this resistance decreases exponentially. So mathematically, it can be expressed by this expression, where this T0 is the 25 degrees Celsius, or in the Kelvin, that is equal to 298 Kelvin. So similarly, this R0 is the resistance of the thermistor at the T0. And similarly, this B is the beta value or the B value of the thermistor. And typically, it is given in the data sheet. So this B value depends on the materials which are used for making this thermistor. And if you see the unit of this B value, then it is in the Kelvin. So in the datasheet, if you see, then this B value is specified over the specific temperature range. For example, if the B value is specified over the temperature range of 25 degree to 100 degree Celsius, then in the datasheet, it is represented as B25/100. Now for the thermistors, this nominal resistance is the value of the resistance of the thermistor at the 25 degrees Celsius. So as you can see from the given equation, if we know the B value and the value of the nominal resistance for the specific thermistor, then we can easily find the resistance of the thermistor at the any temperature. And conversely, if you know the thermistor resistance, then from that we can easily find the present temperature. So now let us see, when the thermistor is integrated with the any system, then how the temperature is measured. So to measure the temperature of the thermistor, first we need to convert this change in the resistance of the thermistor into the voltage. So to measure that change, what we can do? We can pass a fixed current through the thermistor. So depending on the temperature, the resistance of the thermistor will change. And accordingly, the voltage drop across the thermistor will also change. And if we see this voltage drop, then that is equal to I times R. So as you can see, this voltage drop across the thermistor is directly proportional to the resistance of this thermistor. So by measuring this voltage drop across the thermistor, we can convert the change in the resistance into the voltage. Now here, while using these NTC thermistors for the temperature sensing application, this bias current that is passing through the thermistor should be very low. Typically, it should be in the microampere. So if it is more than that, then the effect of the self-heating can occur in the thermistor. So as the current passes through the thermistor, then there will be a power dissipation across the thermistor, and that is equal to I square times R. And because of this power dissipation, the temperature of the thermistor will also increase. So this phenomenon is known as the self-heating. So if more current is passing through the thermistor, then there will be a more power dissipation. And because of that, the self-heating effect will be more prominent. So because of this self-heating effect, since the temperature of the thermistor itself is increasing, so its resistance will further reduce. And because of that, it will not be able to measure the surrounding temperature accurately. For example, without the self-heating, at the given ambient temperature, this should be the resistance of the thermistor. But because of the self-heating, since the temperature of the thermistor itself is increasing, so its resistance will further reduce. That means if the thermistor is operated in the self-heating mode, or in other words, if the current through the thermistor is large, then we will not be able to measure the temperature accurately. And that is why the current through the thermistor should be in such a way that there is a low power dissipation across the thermistor. So the one way to bias this thermistor is using the constant current source. Because with this technique, even if the resistance of the thermistor changes due to temperature, then also the current that is passing through the thermistor almost remains constant. But the issue with this technique is that as the temperature increases, then the resistance of the thermistor reduces. And because of that, at the low temperatures, the power dissipation across the thermistor will increase. And because of that, at the low temperatures, we might see the effect of the self-heating. That means with this technique, if we try to measure the very low temperatures, then we may not get the accurate results. Moreover, in this method, since the output voltage is directly proportional to the resistance value of the thermistor, so with the change in the temperature, this output voltage will also change non-linearly. That means at the low temperature, since there is a more change in the resistance value, so we will get the more change in the output voltage. But at the higher temperature, there will be a lower change in the output voltage. That means with this technique, we will not get the linear response. So if we want to get a relatively linear response, then we can use the another simple approach. So in this approach, we are using a simple voltage divider circuit of the thermistor. So as you can see, here a series resistor Rs is connected with the thermistor, and this series combination is biased with some fixed voltage. So once again over here, this biasing voltage and the series resistor should be selected in such a way that there is a no self-heating effect in the thermistor. So in this approach, as the temperature increases, then the resistance of the NTC thermistor will reduce. And because of that, the voltage drop across the thermistor will also reduce. So in the earlier constant current biasing, this was the voltage versus temperature curve. And as you can see, it was the nonlinear. But here, we will get this S-shaped response with the turning point in the center. So this turning point will occur at the temperature where the resistance of the series resistor is same as the resistance of the thermistor. And around this turning point, the response will be relatively linear. So for example, if the nominal resistance of the thermistor is 10 kilo ohm, and if we select the value of the series resistance Rs also as a 10 kilo ohm, then this turning point will occur at the 25 degrees Celsius. So in this way, by properly selecting the series resistance value around our required temperature range, we can change the turning point. Moreover, by changing the series resistance value, the power dissipation across the thermistor will also change. So as you can see, as the series resistor value increases, then the current that is flowing through the thermistor will also reduce, and hence the power dissipation will also reduce. Moreover, as we increase the value of the series resistor, then this output voltage versus temperature curve will also get more linear. But at the same time, the sensitivity or the change in the output voltage with the temperature will also reduce. So there will always be a trade-off between the linearity and the sensitivity. And according to one's requirement, one should optimize this series resistor value. Now sometimes, to increase the linearity further, this parallel resistor is also added along with the thermistor. So with this, we can further improve the linearity. But along with that, the sensitivity will further reduce. So as I said earlier, depending on the required linearity and the sensitivity, this parameter should be optimized. So once we get this output voltage that is almost linearly changes with the temperature, then with the help of the ADC, this output voltage can be digitized. And the temperature corresponding to that output voltage can be displayed on the display unit. So all these linearization techniques that we have discussed so far are called the hardware linearization techniques. Because here, using the external hardware, the output of the thermistor is made to change linearly with the temperature. So these techniques are relatively simple and the cost effective. But here, we have to compromise in terms of the temperature sensitivity. So in a more sophisticated systems, where we require a more temperature sensitivity, typically a software linearization techniques are employed. So here, even with the nonlinear response of the thermistor, using the curve fitting techniques in the software and using the lookup table, we can get the corresponding temperature of the thermistor at the specific voltage. So using this technique, it is possible to convert the change in the resistance value of the thermistor into the voltage. And in a way, it is possible to measure the temperature of the thermistor. Alright, so as I said earlier, these NTC thermistors are mainly used in the temperature sensing applications. Like they are used in the mobile communication devices for the temperature measurement of the TCXOs, LCDs and the battery pack. Similarly, they are also used in the computer and the consumer electronics. For example, they are used for the temperature measurement of these hard disk drives, the optical disk drives, the LCDs and the medical devices. So similarly, they are also used in the household electronic products and they are also used in the products related to the heating and the air conditioning. But apart from that, sometimes these NTC thermistors are also used as a inrush current limiters at the low and the medium powers. So let us see how it works. So here in the given example, this NTC thermistor is used as an inrush current limiter in the SMPS. So whenever the power supply is turned on, then this uncharged capacitor in the SMPS will act as a short circuit, and because of that there will be a very high inrush current. So initially this NTC thermistor limits the inrush current to the desired level, because as you know, at the ambient temperature this NTC thermistor provides the high resistance. Now as the current starts flowing through the thermistor, then the temperature of the thermistor also increases, and because of that the resistance of the thermistor reduces. So once the circuit is operational, then this thermistor provides the low resistance, and in a way it limits the unnecessary power dissipation in the circuit. So instead of this NTC thermistor, if you use a normal resistor, then also it will restrict the inrush current. But once the circuit is operational, then there will be unnecessary power dissipation across this resistor. So in this way, this NTC thermistor is a better option compared to the normal resistor. Apart from that, it is also used as a basic level sensor. So once again, Here the thermistor is used in a self-heating mode. So in the self-heating mode, because of the power dissipation, the temperature of the thermistor increases. And the amount of temperature increase in the thermistor depends on how well the surrounding absorbs the heat that is generated by the thermistor. So for example, if the thermistor is kept in the air, then the heat transfer from the thermistor to the air will be less. And in that case, the rise in the temperature of the thermistor will be more. But if the same thermistor is submerged in the liquid, then the heat transfer from the thermistor to the liquid will be more. And in that case, the rise in the temperature of the thermistor will be less. So effectively we can say that when the thermistor is in the liquid, then its resistance will be more, because in that case, the temperature of the thermistor will be less. And by detecting the corresponding voltage, we can know that whether the thermistor is in the liquid or not. Or in a way, it can be used to detect the level of the liquid. So these are the other applications of the NTC thermistor apart from the temperature sensing. So similarly, now let us briefly talk about the PTC thermistors. So as we have discussed earlier, these PTC thermistors are used in the applications where we need a sudden change in the resistance with the temperature. So typically, if you see the temperature versus resistance characteristic of this PTC thermistor, then it will look like this. So as you can see, up to certain temperature, the resistance of the PTC thermistor slightly reduces with the temperature. But as soon as the temperature goes beyond the Curie point, then the resistance of the thermistor increases rapidly. So the Curie point is the temperature at which the resistance of the PTC thermistor gets doubled compared to the 25 degrees Celsius. So mainly, these PTC thermistors are used for the overcurrent protection, as well as they are used in the circuits where we need a delayed operation of the relay. Apart from that, they are also used in the soft starter circuits to increase the lifetime of the component or the specific part. And moreover, in the self-heating mode, they are also used as a self-regulated heaters. So in all these applications, these PTC thermistors are used in a self-heating mode. So apart from that, there is another type of PTC thermistor whose response changes linearly with the temperature. So this type of PTC thermistors are mainly used for the temperature sensing applications. And here, by measuring the change in the resistance of this PTC thermistor, it is possible to measure the temperature. So for that, we can use the similar hardware techniques that we have discussed for the NTC thermistor. So now let us see how these PTC thermistors can be used in all these applications. So as I said, they are used for the overcurrent protection. So in the normal operation, the current through the PTC will be nominal, because under the normal operation, the temperature of the PTC will be less than the Curie temperature. So in that case, it will offer the low resistance. But due to some fault, suddenly if the current in the circuit increases, then because of the self-heating, the temperature of the thermistor will also increase. And once it goes beyond the Curie temperature, then its resistance will also increase rapidly. And because of its increased resistance, it limits the excessive flow of current in the circuit. So in this way, these PTC thermistors can be used for the overcurrent protection. Apart from that, they are also used in the applications where the delayed operation of the relay is required. So for that, this PTC thermistor is connected in parallel with the relay circuit. So whenever the voltage is applied to the relay circuit, then initially the current will flow through the PTC thermistor, because initially this PTC thermistor will provide the low resistance. So that is why most of the current will flow through the PTC thermistor. And as the current starts flowing through this PTC thermistor, then because of the self-heating, its temperature will also increase. And once it goes beyond the Curie point, then suddenly the resistance of the PTC thermistor will increase. So because of this increased resistance of the PTC thermistor, now the current that is flowing through the PTC will reduce. And now the more current will start flowing through the relay circuit. So because of that, now the relay gets energized and now it will be in the on condition. So in this way, it is possible to delay the operation of the relay circuit. So apart from that, to increase the life of the component or the specific part of the circuit, sometimes this PTC is also used as a soft starter. So here in the example, it is connected in the parallel to the fluorescent lamp. So initially, when the circuit is turned on, then this PTC thermistor is operating at the ambient temperature, and that is why it offers the low resistance path. So because of that, initially, most of the current flows through this PTC thermistor, and only a very small current will flow through the fluorescent lamp. Now as the current passes through the PTC, then because of the self-heating, its temperature will increase, and because of that, its resistance will also increase. And due to this increased resistance, now the current that is flowing through the PTC will reduce. So now, more current starts flowing through the fluorescent lamp, and gradually it will get turned on. So in this way, by using the PTC in a soft starting circuit, it is possible to increase the life of the specific component. So apart from that, sometimes these PTC thermistors are also used as a heater when the localized heating is required. So these are the few applications of the PTC thermistor. So I hope through this video you understood what is thermistor, how it works, and what are the different applications of the thermistor. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.